Good morning everyone. Welcome to Probability and Statistics for Data Science. So in this course we will study how to analyze uncertainty and randomness using mathematical tools. So probability plays a very important role in data science, engineering and decision making. In this lecture we will begin with the fundamental concepts of probability, which will serve as the foundation for all future topics in this course. In this course, we will cover several important topics such as probability theory, random variables, probability distributions, correlation, regression and hypothesis testing. Each of these topics is essential for understanding how data behaves. Today, we are starting with the basics of probability, which is the first step towards understanding randomness and uncertainty in real-world applications and situations. As we proceed further throughout the syllabus, you will notice that the probability forms the base for everything else. Concepts like distributions and statistical inference depend heavily on probability theory. So it is very important to clearly understand these basics before moving forward. For this course, we will refer to standard textbooks such as those by Ravichandran, Montgomery and Ranga and Veerarajan. These books provide both theoretical and explanations and practical problems. You can use them for deeper understanding and practice. Additionally, reference books like Walbull and outlines of SCOW are useful for solving more problems and strengthening your concepts. Course outcomes. By the end of this course, you will be able to calculate expectations and variances, apply standard distributions, perform correlation and regression analysis, test hypothesis and analyze variance. These skills are very important in data science, where we interpret data and make decisions based on statistical reasoning. So in this unit, we will focus on probability and random variables. Topics include axioms of probability, conditional probability, Bayes' theorem, and different types of probability functions. These concepts helps us understand how random events behave and how to mathematically represent them. So, what is probability? Probability is a branch of mathematics that deals with uncertainty. It tells us how likely an event is to occur. The value of probability lies between 0 and 1, where 0 means impossible and 1 means certain. Probability helps us predict outcomes and make decisions in uncertain situations, which is very important in real-life applications. Experiment and random experiment. An experiment is any process that produces outcomes, whereas random experiment is one where all possible outcomes are known but the exact result cannot be predicted in advance. For example, tossing a coin is a random experiment because we know the outcomes are head and tail, but we cannot predict which one will occur in a trial. So this is the example we have told already. The next one example is throwing an unbiased die in a random experiment. We know in advance that the possible outcomes of the phases are 1, 2, 3, 4, 5, 6, but we cannot specify that which outcome will come in the first and the second and so on. So drawing a card from a well shuffled pack of 52 cards in a random experiment. So we know that the outcomes are 52 and we couldn't predict that which outcome is the first. So these examples clearly shows that how we list all possible outcomes before calculating the probabilities. So in this example, marbles of different colors are drawn. The sample space includes all possible combinations. Events or the subsets of this sample space, so which helps us to understand how probability problems are structured. The definition of the event comes here. An event is a subset of the sample space. It represents a specific outcome or group of outcomes. For example, getting a head in a coin toss is an event. Events are what we calculate probabilities for. The next one is sure and impossible events. A sure event always occurs and is equal to the sample space. Its probability is 1. An impossible event never occurs and it is represented by the empty set with probability 0. These are the cases in probability. The next one is equally likely outcomes. Outcomes are equally likely if each outcome has the same probability. For example, in a fair coin toss, head and tail each have probability by 2. So here the probability to occur head is 1 by 2 and same as the probability to occur is also 1 by 2. So here tossing a coin is a equally likely event. This assumption simplifies many probability calculations. So in a die, all 6 outcomes have equal probability of 1 by 6. Similarly, coin toss outcomes are equally likely. These examples helps us apply the classical definition of probability. The next one is complementary events. The complement of an event means the event is not occurring. If event E happens, its complement does not happen. The sum of probabilities of an event and its complement is always 1. Exhaustive events. Exhaustive events include all possible outcomes of an experiment. For example, a die has 6 exhaustive outcomes. And in tossing a coin, the exhaustive events are 2. This concept is important when calculating total probability. Mutually exclusive events. The events are said to be mutually exclusive if they cannot occur at the same time. For example, getting a head and tail in a single coin toss cannot happen together. These events do not overlap. So all the simple events are mutually exclusive. That is, the occurrence of one of them automatically excludes the possibility of the occurrence of the other in a single observation. So suppose a card is taken from a pack of 52 cards and the events A, B, C are defined. A, the card taken is a spade. B, the card taken is a heart. C, the card taken is a king. So here A and B are mutually exclusive, since if the card is a spade, it cannot be a heart. Therefore, if A occurs, then B cannot occur, and if B occurs, then A cannot occur. A and C are not mutually exclusive because the card can be the king of spades when A and C will have occurred. Similarly, B and C are not mutually exclusive. The next topic is on axioms of probability. The axioms of probability define the basic rules. Rule number 1, probability is always non-negative. Probability of the sample space is 1. This is rule number 2. And probability of pi is equal to 0. Rule number 3, probability of mutually exclusive events are additive. That is, if E and F are mutually exclusive events, then the probability of E union F is equal to probability of E plus probability of F. These are the foundations of probability theory. Next, mathematical definition of probability. The classical definition states that probability is equal to favorable outcomes divided by the total outcomes. This formula is widely used when outcomes are equally likely. That is, probability for an event E is given by the number of favorable outcomes divided by the total number of trials. Example, tossing a coin every time followed throwing a dice are called the trials. Then the results of the classical probability is given by the probability of an impossible event is 0 and the probability of the complementary event A bar of A is given by P of A bar is equal to 1 minus P of A. These two conditions we have seen already. So when two coins are tossed, the sample space has 4 outcomes. Only one outcome gives 2 heads. So the probability is 1 by 4. This is the simple application of classical probability. So here P of E is equal to N of E divided by N of S, which is 1 by 4. So N of S is total number of trials, which is 4, and favorable cases is 2 heads, that is only 1, so which is 1 by 4. The next one, a die is rolled. Find the probability that the even number is obtained. In a die, we have the sample space. S is 1, 2, 3, 4, 5 and 6. Let us consider E as the event that must obtain an even number, that is 2, 4 and 6. So the number of favorable outcomes is 3 divided by total number of trials is 6. So probability of E is equal to 3 by 6, which is 1 by 2. Let us consider another one example. A card is drawn at random from a deck of cards. Find the probability of getting 3 of diamond. In a deck of 52 cards, probability of drawing a specific card like 3 of diamond is 1 by 52. So N of E is 1 and N of S is 52. So this shows the probability of E is 1 by 52. This shows how probability works with larger sample spaces. So what is the chance that a leap year selected at random will contain 53 Wednesdays? So in a leap year we have 52 Wednesdays and 2 days left. 52 weeks have 52 Wednesdays, and we have to check for what if the condition that satisfies the 2 days. So these 2 days can be either Sunday, Monday, Monday, Tuesday, Tuesday, Wednesday, Wednesday, Thursday. Yes, Thursday, Friday, Friday, Saturday, Saturday, Sunday. So we have to see for 53 Wednesdays. Already we have 52 and there are 7 days in a week. So out of these total 7 outcomes, the favorable outcomes are 2. So that is 2 options, either Tuesday, Wednesday or Wednesday, Thursday. So 2 outcomes are there. So hence the probability of getting 53 Wednesdays in a leap year is 2 by 7. So similarly, the example of a bag contains 10 white, 6 red, 4 black and 7 blue balls. 5 balls are drawn at random. Find the probability of 2 of them are red and 1 is black. So the total number of balls is 27 balls. So here 5 balls are drawn. From these 27 balls, in how many ways? N ways. So 27 C5 ways. So that is nothing but 80730 ways totally are there. that is the total number of exhaustive events, and we have to draw 2 red balls can be drawn from how much red balls totally are there? 6 red balls are there. So out of 6 we are drawing only 2, so 6 C2 ways occurs, and 1 black ball is drawn from 4 black balls in 4 C1 ways. So the total number of favorable cases, that is 2 red balls and 1 black ball, is 15 into 4, which is 60 ways. So the remaining 2 balls can be chosen from 4 black and 7 blue balls in 11 C2 ways, that is 55 ways. So therefore the total required probability is nothing but number of favorable cases divided by total number of exhaustive cases, which is 3300 divided by 80730. So until now we have learnt about the axioms of probability and what is probability, what is the classical definitions of probability, etc. So here in this lecture we covered the basic concepts of probability which are essential for further study. So in the forthcoming sessions we will continue with more interesting topics. Thank you.